Basically, we have one more thing today and then the overview. And this typically creates problems, what comes now. Whenever we include that in the exam, and we've done a few times, we have a nice distinction of people between those who can do it and those who cannot do it. And but it's an important thing. I know it can be challenging, but it's really important. And this is where we take the step towards real life applications, machine learning applications, filtering, where there could be many, many X's. Because we need to think about something here. First of all, MLR, multiple, that's short for multiple linear regression, that's one Y and a lot of X's, more than one. Technically, mathematically, breaks down. If, I use some other words here, then if the data, the X data, comes with what we could call exact linear redundancy. So X data is a number of X columns, right? If by some way we could have that can happen in real Excel sheets. Maybe people just store a lot of columns. Maybe some of them are more or less the same information. As long as it's just an Excel sheet, it doesn't hurt to have a lot of columns in the Excel sheet. What if you, for some odd reasons, had both the height in centimeters and the height in meters? Those are pretty closely related, right? By a fixed factor of 100. One is, so that's what I mean by exact linear redundancy. I have two columns there, not the same, but they are having a correlation of 1. If you plot them, they are exactly on the line. They are, one is coming as from the other by a linear transformation. It could also, if you add up the height and the weight for some reason, if you thought that would be relevant. Now I want another number for the size of persons, so let me add the height and the weight, just additively. And that would also be a problem if I have height, weight, and the sum of height and weight. Those three are together are sort of exact linear redundant. They don't have full rank. They are exact collinear, would be another word to say it. That's just to make a little bit, that maybe you'll say, well, then I'll just not include one of them, and that's also a good idea. But then, what happens very often in real life data settings, especially in big data, when you collect observational data, machine learning applications, a lot of other observational data applications, we would also get problems, and that's the collinearity issue. Maybe if X doesn't come with exact redundancy issues, but with near redundancy issues. For instance, what if we have both the weight of persons and the BMI of persons, which is expressing the weight, but not exactly as a relative to height, right? So they're not exactly the same, but they would often be quite correlated if you check the relation between weight and BMI from person to person. People with high weight tend to have high BMI for obvious reasons. Then it's not exact because we are at different heights, and that does give a bit of variability to it. If you put both of such very similar X variables into a regression, now I'm thinking of those two as two X variables, of trying to model something yet different again. We are having this collinearity issue where we have a challenge. Right? There is a challenge we need to deal with. What could happen then if I have two highly correlated X variables? It's related to the understanding of the interpretation of the betas in a multiple linear regression. You know, I had a full slide where I emphasized coefficients in MLR are unique effects where you have corrected for all the other variables in the model. Think about this. If I put in two X's that are sort of more or less copies of each other, more or less contain the same information, weight and BMI, and it could even be worse than that, then I try to do a regression where there is some Y that is a function of weight and BMI and maybe something else also. Then I try to ask the function to give me the relation, the effect of weight having corrected for BMI. or the effect of BMI, having corrected for weight, they seem to be competing a little bit of giving the relation here, right? Because they are almost the same. So it's actually pretty ambitious to ask the model to give the unique effect of weight, having corrected for BMI, and so that could pose problems. What may happen is that when they are both of them there, maybe none of them are unique, right? They are both there. So if weight is there, I don't need BMI maybe, right? And vice versa. If BMI is there, I don't need weight. And that would be the output of MLR if you just look at it. None of them might be significant, clearly not significant, because none of them have a unique effect. But you need to realize that it could be because that the two x's are closely correlated, the collinearity issue. So, and the way to make sure is actually to follow our backwards elimination procedure. That would actually help you. And if you try to think about what happens, and I'm just warning you against what might happen, and it's counterintuitive the first time you see it maybe. Because what could happen then if I take out BMI from the model? Krang! Weight appear important suddenly, right? Or if I took out weight from the model, BMI would be important. So separately they are important, but together they appear non-important. So that's just for us to remember whenever we see something in an MLR, things that appear non-important might not be a global proof that they're not important if I actually, because it could be due to competing, sort of trying to compete with each other among the x's, the collinearity issue. It's a challenge in understanding what we can, how we can interpret the MLR model, and it's sort of an abstraction beyond the basic level in a way. We have a little example. I think we can spend 5 minutes on that. Don't know if it's the best example, but it's an attempt. Let's try to put some words on it here with the colors and then go to R and do it. So we generate some artificial data with 100 observations. Actually, we need to go look at it, otherwise it doesn't make much sense, I think. Here's the prediction code you can copy in when you want that. So here's the last example, my toy example. This is just some X values that comes. It could be an engineering example of some dynamic data like this, some fluctuating data. Some X values there. And I do my second variable. My second variable, I simulate that as a copy of the first one with a little bit of noise. So it's two very closely related variables. And if I plot x2, it looks exactly like x1. Actually, we have the room to do that, so I could also... Yeah, x2, x1, copies of each other with a bit of noise difference. And here's the scatter plot of x1 versus x2, sorry, x2 versus x1, showing the collinearity issue. So showing the fact that x1 and x2 in this case are highly correlated, right? So I'm constructing such a case that I was mentioning in my slide from before. Then I make up the model myself. I make a two-dimensional MLR where I simulate my y values with the slope of 1 on the x and a coefficient of 1 on the x1, x2, sorry, and some random noise of size 1. So I construct my y data to be a multiple linear regression model of those two. What happens then if I plot y against my x1 and x2? Well, what I expect, they are related, right? Clearly relation from between y and x1, y and x2. Positive correlation. What's the correlation? Guess the correlation. 0.75, someone says. Any higher, any lower? 0.6. 0.84. Pretty high correlation. Anyway. Let's try to look at the MLR on the 2. Let's try to do it again. I didn't like the result here, so I'll do it again. That's better for my point to be made. Look at the result of the MLR. They're non-significant, right? Look at what happens if I take out, which one should I take out? If I was following my principle, I should take x2 out, actually, here, right? So I would go for the model with only x1. Is it significant now? Whoa. From not at all to something that could give you the Nobel Prize if it was important enough. But what about if I by chance took the other one out? Took x1 out instead? Well, same story for the other one, right? I'm just showing you what I was telling you could happen a minute ago, right? It should worry us a little bit in the way we interpret also the end result of a backward model selection procedure, of course. And we should be careful about how we interpret those things, right? Because the fact that we left something out could just be due to the fact that by chance it was just a little bit worse off than the other one, but maybe it could just as well be picked up the next time. So that's a challenging task to understand multiple linear regression models, especially also after we do modeling routines. But we must sometimes do those modeling routines to have something feasible. So this, I assure you, if you find it challenging, don't worry, the rest of the world finds it challenging also and discusses it still. What to do, how to interpret, what you're allowed to do, and what you're not allowed. And as many things in the world today, there is no global consensus agreement about that either. God damn it. If we can control, now this is just the fact of life sometimes, that data comes like this in observational studies where things are related and we have a generic challenge in how to interpret the models. If these numbers were something we could control ourselves in a design study, we could do better. We could actually design a study where I make sure one is 0 when the other one varies, and the other one is 0 when the first one varies. If I could decide the x1 and x2 myself, I could make sure that they are varying in an independent way from each other. I could construct an exact pattern, so-called independent or orthogonal pattern between the two in a nicely designed way, such that they basically have 0 correlation. In such a situation, I can nicely find the separate effects because they don't correlate. I don't have a collinearity issue anymore. But that's only for cases where I decide the x's myself. That shows the strength of designed experiments. So when you can do it, it's fine. But I'm not all cases where you want to do such modeling allows you to actually do things like that. So that's a distinction between planning, designing experiments or not. We are almost there. We have, it's important how experiments are designed. We have 2 more questions to, and then sort of the overview. Let's do this one. What do we assume? Same question as last week, actually. So it's the same answer also. So good job there, most of you. Nice name. We have one more little thing to do.